Okay, good morning, everybody. So in the last class, we were looking at, we ended the last class by looking at the printf family of functions, in particular sprintf. Right, so remember what sprintf does, it lets you take data and basically put it into a string, right? So you can print data into a string. It's a common occurrence where you want to do the opposite. So you've got data in a string and you would like to get it back out. So for example, suppose you have the string 2023-01-29 and you would like to extract the values in the string as unsigned values, right? The year, the month, and the day. Right, and so in this particular, so when you're in the situation where you know the formatting of the data that you're trying to extract, so in this case, 4 digits followed by a hyphen, followed by 2 digits, followed by a hyphen, followed by 2 digits, you can use this function called scanf to extract the data from the string. Right, so printf, print into a string, or sorry, print, the various scanf functions let you extract data out from a string. So scanf will scan a string, allowing you to extract relevant data from the string. It works in a way that's pretty similar to the printf family of functions. So for example, here, that thing called buffer, that's the string that you're going to read and try to extract information from. There's a formatting string. So the formatting string is similar to the formatting strings that you would write with printf, but the rules are a little bit different in some cases. And then finally, there's this ... So the ... in C indicates what are called variable arguments, or var args. And so that means that this function here can accept 0 or more extra arguments. So remember what scanf is supposed to do? It's supposed to extract information from a string, right? So if it's going to extract information from a string, it needs to store it somewhere. It's going to store it in whatever extra arguments you pass. Now remember, if a C function wants to write data into an object owned by the caller, the caller needs to pass in a pointer to their variables. The function has to dereference those pointers to write into those variables. So these arguments here, these are called the receiving arguments. These are all pointers to variables where the function can write the data into. Right, so these are all going to be pointers over here. All right, so let's see. The return value, this is important. So the int here. The return value is useful if you're trying to do some error checking. So the return value is equal to the number of receiving arguments that are successfully assigned to. So in your formatting string, what's going to happen is you're going to have one or more conversions, right? So percent something, percent something, percent something, so on and so on and so forth. Right? Each one of those conversions will correspond to one of your pointers that you pass in over here. Right? If scanf fails to convert, if scanf fails to convert any one of your, if it fails to convert data from the string that it's reading, it doesn't write it into the variable that you get. It doesn't write it into the pointer that you, it doesn't write into the object that is pointed to by one of your receiving arguments. Instead it stops, and then it returns the number of receiving arguments that were successfully assigned to. Right? And so you can use this thing for error checking, right? You're trying to read something that you're expecting to have a certain format. If you fail at some point to read some piece of data, scanf tells you, right? I failed to read the second value, for example. It returns 0 if no receiving arguments are successfully assigned to. Right? So if it can't convert anything in your string, it returns 0. Right? And then finally, it returns EOF, so that's short for end of file, if the end of the string that it's reading is reached before any conversion is even attempted. Okay. So let's take a look at an example here. So here's my date that I would like to extract the information from, right? So I have to specify the formatting of the data in that string in order for scanf to extract that data. And so how's this formatted? Well, it's an unsigned integer, right? So %u followed by a hyphen, right? So there's the hyphen, right? Followed by an unsigned, followed by an unsigned integer, followed by a hyphen, followed by an unsigned integer. So our formatting string is %u hyphen %u hyphen %u. Anything that's not a conversion specifier is not stored in the receiving argument, right? So these hyphens, these aren't stored in any of the receiving arguments. So what you need here is 3 receiving arguments, 1 for the year, 1 for the month, and 1 for the day. Right? Now remember, we actually need a variable to write into, so we really do need an unsigned int to write into. Right? So we need the, so here are our 3 variables that we're going to ask scanf to write into. Right? When you call scanf, you have to pass in the address of those variables. Right? It requires a pointer because it wants to write the information into a variable owned by the caller. Right? So we pass in a pointer to the year. We pass in the address of year, the address of month, and the address of day, and that lets scanf write into year, month, and day. It always returns the number of successful conversions. Right? So if the number of conversions is EOF, what does that mean? Well, it means we got to the end of the string that we're reading and it didn't even attempt a conversion. If the number of successful conversions is 0, well, I mean, that's also a failure case, right? It did not successfully convert anything. Right? It tried to, but it didn't manage to perform a conversion. Right? So the case where it returns EOF means that scanf didn't even bother to try a conversion. If it returns 0 or more, it means it attempted to perform a conversion but failed when it tried to do so. Right? So if we get 0, that means there were no successful conversions. If the number of conversions is greater than 1, right, then I know that the year was converted successfully. Right? If it's greater than or equal to 2, I also know that the month was converted successfully. And finally, if it's equal to 3, I know that the day was converted successfully. Right? And so if you pass in that string there, everything should work just fine, right? We get the year, the month, and the day out properly. If we fiddle with the string a bit, so let's get rid of the hyphen and replace it with a space. Here we only get the year and the month, so we know that only 2 conversions were successfully performed. Put the hyphen back, well, let's get rid of let's put all spaces in. Right, so now only the first conversion will successfully happen, so only the year will successfully convert. Right, and if we do something like minus in front, what do we get? We get, oh, interesting. We get the year equal to minus 429,496,5273. So what the heck happened here? Right, that's a signed integer. Right, and so when scanf does the conversion to unsigned integer, right, we get the wrong value. Right? We converted a signed int into an unsigned int. That's not going to work properly. Right? So let's try something else. Try the a in front. And we get no successful conversions. Right? So it attempted the conversion. Right? It saw the a, it tried to convert that to unsigned int. Right? It failed, so we get the 0. The case where you get, so to be honest, I forget all of the cases where where you get EOF. One for sure is if it's the empty string, I'm pretty sure. Yes, so that one is a case where you get the EOF returned back to you. Right. And I forget the other situations in which you can get EOF back from this function. But anyway, there's scanf in a nutshell. Okay, so the next paragraph here explains everything that happens if you need a review. Oh yes, conversions. This is fun. So the way that that scanf behaves is a little bit funny. So most of the conversions that you attempt will consume and discard leading white space before attempting to perform the conversion. Right? And so by consume, I mean it actually looks at the characters in your string, right? Discards them if they're spaces. So here, do I actually try to do it anywhere? No. So let's go back up here. Let me put in the date again, 2020, well, let's put in today's date, 2024, 11/07. So %u will discard any leading white space. So we put in a bunch of white space and attempt and run the program. The conversions happen successfully. Right? So leading white space in front of a value that gets converted is discarded, at least in the case of %u. Any of the numeric conversions, I believe, discard the white space. Right? Afterwards, though, so let's see what happens here. Okay, so if there's space after 2024, right, that doesn't match the plain old hyphen, right? So in this case, the white space is not discarded, right? It's trying to match the literal hyphen, so that doesn't work, right? Oh, sorry. But any spaces in front of the numbers in this case, sorry, will still result in a successful conversion. Right, so that for example, if your data looks like that, that program above will successfully parse the date out of the string. Okay, so characters in the format string that are not part of a conversion specifier, so they're not part of the percent blah 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 blah, they have to be matched exactly, unless you're trying to match white space. So white space is another exception, right? So again, the hyphens must appear immediately after each unsigned int. So that's why the when I put spaces in front of the hyphens, the conversions didn't work. Right. The exception here to the rule is that if you put a space in the format string, the space matches any sequence of 0 or more white space characters. So that's fun. All right, so let's put a space in before the hyphen then, and a space in before this hyphen. And now we can stick in a bunch of spaces here and here. Oh, go away. Here. All right, and let's see what this does. That successfully works, right? Or that works, I guess, right? So the fact that there's a space here means that it's willing to accept any number of spaces before the hyphen, including 0. So this will also work, right, like that. So you have to be a little bit careful about white space in your string when you're parsing it, and white space in your formatting string, right? You have to remember what exactly is it that scanf will do when it encounters white space. So the rest of the notebook goes through the most common conversion specifiers that you might want to use. %s is notable. So %s will convert a string, but it matches, when it converts a string, as soon as it encounters white space, it stops. Right? So if you have the string ABC space DEF, and you want that all read out as one string, you can't use %s. Right? %s will read the ABC, it'll stop, write the ABC into your receiving argument, right? And then it'll want to write the DEF into another receiving argument, right? So %s matches any string not containing white space characters, right? You always get the null terminator written into the string, into your receiving argument. Right? Okay, so the question is, well, what happens if you want to read a string that has white space in it? You're stuck with the %c conversion. So %c matches a single char, but you're allowed to specify how many characters you'd like to read. So %c does not discard white space, right? So that's the thing you need to, that's what you want to use if you have to read something that's got white space in it, and the white space is significant for your data. Okay, so the next program here goes through all of those examples, and it also tells you about the % bracket conversion. For the purposes of this course, I don't think it's important that you know all of these conversions. You have to do the basic stuff, right? You have to be able to convert a string, you have to be able to convert an int and a floating point number, right? All of this other stuff, it's too hard to remember, right? You need the documentation in front of you to do this with any confidence, right? And I'm not going to give you all the documentation for scanf, right? It's this gigantic page of stuff. So this here, the rest of the notebook is here for your information only. Right? And there is actually a fair bit of extra information in this notebook, right? Don't commit it to memory. Right? Alrighty, so that wraps up the strings notebook. Any questions before we move on? Okay, so the next notebook is dynamic memory allocation and deallocation. And so this is where we finally learn how to use arrays properly in the language. Right, and then after this lecture, this will also let you successfully build interesting data structures in C. All right, so memory allocation and deallocation. So when you create objects, or when you ask for memory, you're basically asking C, or you're basically telling C that you want to control over the lifetime of this object. Right? So when you ask for memory, you also are responsible for giving memory back to the operating system. And so whenever you allocate memory, your objects are said to have allocated storage duration. Right? The programmer is now responsible, or now takes on the responsibility of controlling the lifetime of the object. Right? So what does that mean? It means the programmer has to, so if you think about this in terms of Java, right? So in Java, an object is born, it's used, and then it dies, right? The programmer is only responsible for asking for the object to be born and using the object. They don't care about the death of the object, right? So the same is true, in C, the programmer is now also responsible for getting rid of the object, right? Removing the object from memory, returning whatever resources the object used back to the operating system. So to make a dynamically allocated object in C, the programmer asks for memory, right? Typically that ends up going to the operating system, so you ask the operating system for memory, right? You assign a value to your object, so when you get asked for memory from the operating system, the memory is either not initialized, right, or it's initialized to all zeros, depending on which function you call, right? So you probably need to assign a value to your objects before you use them. Right? You're then going to use them as required, so now they just become objects and you can use them however you want. Right? And then when you're done with them, you have to release the memory and whatever other resources are used by your objects back to the operating system. If you don't release the memory used by your objects, right, the operating system never gets that memory back until your program ends. Right? If your program is constantly allocating objects and not freeing them after when they're done, eventually you'll run out of memory. Okay, so now in C, the programmer has yet another responsibility. They're now also responsible for controlling the death of their objects. Okay, so there's only a small number of functions you need to know to use C's dynamic memory allocation and deallocation. So the three allocation functions that we're concerned with in this course are malloc, calloc, and realloc. There are other ones. So there are these aligned, free, and free aligned. We don't care about those in this course. They're beyond the scope of what this course covers. So you need to know the three up here. So all of these functions, they do something similar. They all allocate a chunk of memory, and they all return a pointer back to the start of that chunk of memory. Right? And so in other words, the programmer can then access the memory via a pointer. Right? When you're done with the memory allocated by one of these three functions, you're supposed to call the function called free. Right? So you call free, you pass in a pointer to the start of the memory that was allocated for you. So in other words, you pass in the pointer that was returned by one of these three functions. Right? Free is then responsible for releasing the memory used. Okay, so what does malloc do? So malloc, it's pretty easy to use. Right? You just call malloc and you ask for some chunk of memory. Right? Size is the size is a multiple of the number of size is a multiple of car, right? How many bytes of memory you would like. Malloc returns a pointer to the start of that memory, right? So notice it returns void star, so it returns a void pointer, right? You're allowed to store, you can store that pointer in whatever pointer object you want, right? So if you ask for enough memory to hold an int, you can store this pointer in a pointer to int. Right? If you ask for 10 doubles, you can store this pointer in a pointer to double. Right? You don't have to cast, and it's recommended that you don't explicitly cast the return value of malloc. Okay, so technically malloc can return null. Right? So in other words, that pointer can be null if malloc fails to allocate, or if malloc fails to get enough memory from the operating system to meet your request. Right? Technically. It turns out in Linux, malloc never returns null. And in fact, in any common operating system except Windows, malloc never returns null. In other words, malloc always says it succeeds, even if you allocate an enormous chunk of memory. Right? Malloc says, yes, here you go. Right? Do you actually have that memory? Probably not if it's really big. Right? So in other words, you might encounter a failure later on. Is that true? Something funny will happen later on, right? If you try to allocate a huge chunk of memory. Possibly. Okay. All right, so here's an example of using malloc. Notice we have a structure up here, right? So 0.2 is also here. Okay, so malloc, you pass in the number of bytes of memory that you would like. So malloc 1 allocates enough memory for 1 car, right? What's the return value? Well, the return value is a pointer to something, right? So here, a pointer to car would be a suitable return value, right? Now, once I've asked for memory here, right? At some point, I have to free the memory that was allocated here, right? If I don't, there's a problem, right? Or there is potentially a problem, right? Okay, so I've now got a pointer. It points to 1 byte of memory. So what can I do with it? Well, I can dereference it and treat that memory as though it were a car. So I can dereference C, right? That now is the object that is sitting in whatever memory malloc allocated for me, right? So I can store a character in that memory, no problems, right? I can even print that character afterwards, right? So dereference the pointer again, right? And when I do that, right, we successfully print out C. When I'm done with C, so in this case I'm done with C pretty quickly, right? Because this is just an example. I should free the memory that was allocated by calling the free function here, right? Typically you wouldn't do something like this, right? This is just an example, right? So typically you would use the memory that was allocated and stored in C, right? Sometime later in the program, when you're done with it, you would eventually free it. Okay, so what happens if you want to allocate enough memory for something else? So say an int, well, that's what size of is for, right? So if you want to allocate, dynamically allocate an int, or memory for an int, right? You ask for a block of memory that can hold an int. You store the return value in a pointer to int, right? And now you can treat that memory as though it were an int, right? So I can dereference that memory, or dereference the pointer, sorry, and store an int in that memory. Right, if you print it out, you get 99. So all these examples work just fine. Right? You want a double? Well, you ask for a memory that's the size of a double. Right? You'd like a structure? No problem. Ask for a memory that's the size of a structure. Right? Remember with structures, once you have a pointer to a structure, you get to use the arrow notation. So you don't have to dereference the pointer. Use the arrow instead. The arrow dereferences it for you. So s arrow x sets the x component to 0.5, s arrow y sets the y component of our structure to minus 9.9. Right, and all these examples work just fine. Okay, so what happens if you want to allocate an array? Well, no problem. You just, if you want an array of length n, you just multiply it by the size of your element type. So here everything's going to be, oh no, n's going to be 8. So I'd like to allocate a string, or memory for a string that can hold 7 characters. Right? So what do? Well, you call malloc. Right? You pass in the number of bytes that you want to allocate. So 8 times size of car, which is just 8. Right? I can now treat that memory as though it were an array of car. In fact, I can treat that memory as anything I want. Right? I know that it's 8 bytes big. Whatever fits inside that 8 bytes, I can stuff in there if I want to. Right? There is a way to do it. Right? So here I'm going to treat it as though it were just an array of car, so 8 characters. What can I do with an array of car? Well, I can treat it like a string. So I can copy the string, sys220, into my newly allocated array. Right? If I print out the string, not surprisingly, you get sys220 right down here. Right? And of course, the string pointed at by C is completely independent from our string literal sys220. Right? If I change the characters of C by using the pointer, right, that does not change the characters of the original string. Okay, what happens if I want an array of ints? Well, exact same thing. Right? I want 3 ints, so it's just 3 times size of int. I can now treat the memory, I can now treat I, right, as though it were a pointer to 3 ints. Or I can treat I as though it were an array of size 3. So I0 is 1, I1 is 10, I2 is 100. Print out the elements. Everything works just fine. Right? Similarly for doubles, right? I would like n doubles, so in this case 3 doubles, so n times size of double, right? D is now a pointer to an array. D is now points at 3 double values, right? So I can treat those 3 double values as though they were an array of double. Right? And finally, you can do the same thing with structures, right? So I would like n, so in this case 3 points, right? Or memory to store 3 points. You have to be a little bit careful here with this one, right? So you have to remember now that S is a pointer to three structures, the 3 point structures, right? So if you use the arrow, so if you write S arrow X, that sets the value of the first point, right? If you want to set the values of the second and third points, you either have to use some pointer arithmetic with S, or you use the array notation, right? So go in to the second point, right, and change its x coordinate, right? So notice here I'm not using the arrow notation here, right? S1 is the second point object, right? It's not a pointer to the second point object, right? It is the second point object. So here I have to use the dot to access its x coordinate, right? So S here is the pointer, right? S1, not a pointer, right? It's actually an object. And so here you can see that the points are also printed out correctly. Okay, so that's how you dynamically allocate an array, which solves the problem of how do you write a function that returns a new array, right? Well, dynamically allocate a new array inside your function, return the pointer that malloc gives you. Right? So if you want to return an array from a function, remember you can't make a regular array inside the function and return the regular array. Right? That doesn't work. The array disappears when the function returns. So here's a situation where you must use dynamic memory allocation. So int array returns an array having that many elements, that many ints in it. Right? So how does this work? Well, okay, so the first thing you have to be careful with these sort of functions. So you have to remember that in C there are no zero length arrays, right? Which means that when you call malloc, you're not supposed to pass in the value 0. Right? Exactly what happens depends on your implementation of malloc. I'm pretty sure on my computer it works, and you get back an object of size. You get back, if you pass in 0, you get back 1 byte of memory. So I'm pretty sure it works, but you're not supposed to pass in 0. So here I'm going to check. Right? If the length is 0, I'm going to make the length 1. Right? I'm then going to allocate my array. Right? This one actually initializes the first element of the array, I guess. We're going to write in -99, and then we're going to return the pointer that was returned by malloc. Right? And so now the caller gets back an array of that size. Right? More precisely, they get back a pointer to that many ints, which they can then treat as an array. Right? So here, A is a pointer to 10 ints. Right? I can treat the values of I can use A as though it were the name of an array, right? A0, A1, A2, up to A9, right? And away you go, right? So this one will do what you expect it to do, right? So it gives you back an array of length 10, right? The first element is -99 because our function set it to -99. No, so what you have to remember is that malloc does not initialize the memory that's returned. So whatever memory happens to be sitting there, those are the values that are now sitting in your array. So if we try to print out a 1 through 9, you could get anything. And I'm not exactly sure what we're going to get. So let's see what happens when we print out the 10th element of the array. So we get 0 in this case, right? You have to be careful when you do this sort of thing, right? When you write these little toy programs, you often get a deceiving result, right? If you conclude that the elements of A are actually all zeros, you're wrong, right? If you call this function enough times, you're eventually going to get back an array where the elements are all uninitialized. And so your values are not guaranteed to be set to 0 by malloc. Okay, so what else could you do? So there we returned an array, right? Now remember from the previous lecture, maybe the one before that, there is another way to do this, right? So another way to do this is instead of returning an array, you can ask the caller for a pointer to an object where we can store a pointer to the array. Right, so one more time. We can ask the caller for a pointer to an object where we can store the pointer returned by malloc. Right, so what does that mean? The caller needs to pass in a pointer to a pointer, which is what that is. Right, int star star is a pointer to a pointer. Right. This is going to do the exact same thing. Right, it's going to allocate the array using malloc. It's going to write a value into the first element of the array. Right, and now instead of returning buff, right, I'm going to write the value of buff into ARR. Right, what's the value of buff? Buff's a pointer, so it's a memory address. Right. So I want to write the value of buff into a pointer to int, right? That's owned by the caller. If I want to write a value into a variable owned by the caller needs to pass in a pointer to that variable. So they need to pass in a pointer to int. Right? So down here, caller makes a pointer, right? They call int array, passing in the address of the pointer. Right? This is fine, right? Int array is going to dereference the value that's passed up here. Right? That gives us A. A is a pointer to int, so I can write in a value that's also a pointer to an int. Buff is a pointer to an int. Right? And now the caller can use A as though it were an array down here. Right? So this also works. Right? Just fine. Right? Right? So if that seems slightly confusing, it is. Right? That's because it is. Right? It is a little confusing. Typically, if you're going to write a function like this, you'll return a pointer instead here, and you'll ask the caller to pass in a pointer to a value where you can write in the length of the returned array. Right here, we don't have to because the caller is asking us for an array of length 10. Right? But if your function is going to return an array where the result depends on some calculation that the caller doesn't know the value of, right? The caller still needs to know how big is the returned array. So somehow you have to communicate that second piece of information back to the caller. Right. Okay, so there is a little explanation here about the pointer to pointer syntax right there, right? If you need to hear that if you need to read about that another time. All right, so we'll skip over that again. All right, so malloc can in principle return null. Right, so it returns null if malloc fails to allocate enough memory for you. Right, so the normal advice that you'll see is that you should always look at the return value from malloc before you use it. Right, so in other words, you should never use a null pointer. Right, malloc returns a pointer, it might be null. Right, so in other words, you should always check the pointer. Right, so you call malloc, we store the result in a pointer str. Right? If str is the null pointer, something has happened. Right? So in other words, malloc has failed to allocate 1,000 bytes for me. That's what it's saying. Right? 1,000 bytes is not very big on a modern computer. Right? So the question is now, well, what on earth do you do? Right? Basically, your computer has run out of memory if this has happened. Right? Is there anything reasonable that you can do at this point? Probably not. Right? Your computer's out of memory. What's your program going to do? Right? You needed that much memory to proceed. You're out of memory. Is there anything you do? Probably not. There are situations where you might be able to do something, but beyond the scope of this discussion. Right? So what on earth do you do now? And so now, if you ask people, well, what do I do if this happens? Right? They'll just tell you it depends, which isn't very helpful. Right? That's not very helpful. That's not very good. That's not very helpful advice. So. So the basic line of thought is that if your allocation function has failed because the operating system can't satisfy the memory request, you're basically stuck. So the idea is that your program should probably clean up and shut down because there really isn't anything else you can do. Right? And so that's what the exit function is for. Right? So what you should do is the program should release whatever resources it has allocated and then shut down cleanly. Right? And so the exit function can be used to cause normal program termination. Right? So in other words, it stops your program in a quote unquote clean way, right? And returns the exit status back to the caller, back to the operating system. Right? So in C, exit, if you have what's called an open stream, so in other words, if your program's open some files to read or write to them, exit will close those files, right? So that they're not in some funny state. Right? It then terminates the program and it returns the exit status back to the operating system. Right? So often you'll see something like this. Right? This is what you'll see for advice when using malloc. Right? You'll print an error message, right? And then you'll exit. Right? This looks great and everything, except printing the error message probably takes memory, and you just ran out. So will fprintf succeed? Who knows, right? So I mean, this advice is not super useful, right? All right. So if your program is more sophisticated, so if you're writing a program that needs to run for a long time, you might be handling the memory allocation yourself. And so in other words, your program might allocate a chunk of memory for itself when it starts up. And then in those situations, you might be able to free some of that memory back if malloc ever fails. Right? So more sophisticated programs might be able to handle low memory situations differently. However, right, Windows is the only commonly used operating system where malloc might actually return null on failure. Right? In all other common operating systems, so that includes Mac and Linux, all versions of Linux as far as I know, malloc never fails. Right? It'll never return null back to you. Right? If there's a low memory condition, so if your operating system really is running out of memory, right, then your program has no say in the matter. The operating system starts shutting stuff down. Right? So your program can't do anything about it anyway. And so if you're not writing for Windows, there really is no point in checking for null on failure. Right? And so there's actually a research article that link points at. That if you're interested, you can read about it. Right? The authors of that article claim that you should checking for null is not useful. Right? So what you do in this course is, I don't care. If you check for null, that's great. Right? If you're not checking for null, that's also fine. What you do when you get out into the real world, it depends on who you're working for. Right? So you ask your boss, what should I do? And you just follow their advice. Right. Okay, calloc is basically like malloc, except it also zeroes out the memory that's allocated. Right. You call it in a different way, right? So calloc, you ask for that many memory for that many objects. Each object has that much size, right? So whereas malloc, you multiply the number of elements by the size, calloc does that calculation for you. Right. Otherwise, it's exactly the same, right? Everything's exactly the same, and it also initializes the memory to 0. Right. So the exact same example, if I want a memory for one character, I can ask calloc memory for one character. Right? If I want memory for one int, I can ask calloc for memory for one int. Right? One double. Right? 1.2 structure. Everything works exactly the same way. The extra bit of information that you get from calloc is that the memory is guaranteed to be initialized to all zeros. Right? All the bits of the return memory are 0. Okay, so here is this is the same program as before. Well, almost the same. So this returns an array of unsigned int, right? That many of them. So if you want to make an array of length unsigned ints using calloc, right, you ask calloc for that many unsigned ints, right, and we return the array. So in this case, I'm not setting a value in the array. I'm just going to return the array, right? I know the returned array is all zeros, right, because I used calloc. So if you run this program, right, and if you were to print out all the values of the array, they would guarantee to be 0. Don't forget to free the array when you're done, right? So there's a call to free. So notice in these little toy programs that I'm showing you, everything's happening in main, right? So we call a function, main runs, right? Then you free the memory here, right? Because the array was allocated in main, right? If you don't free the array here, when the program ends, all the memory that was allocated by the program gets returned back to the operating system anyway. right? So technically, this call to free here, not really important, right? But in most situations, you're not writing a little program that looks like this, right? You're using an object, some function somewhere, right? Some other function needs to get rid of it, so that other function has to get rid of the object by calling free, right? Okay, realloc. So there are occasions when you've allocated a block of memory, later on you decide it's either too big or too small, right? And so you want to reallocate that block of memory. So by reallocate, I mean you want to keep all the values that are in that block of memory, right? But you want to change its size. So that's what realloc is for, right? So for example, if you're implementing an array-based list in C, right, and you're adding elements to the array, eventually you'll run out of space in the array, right? So what do? You make a new array that has all of the elements of the old array that's bigger than the old array. That's what realloc is for, right? It makes the new array, copies all the elements that are in the existing array into the new array, returns back a pointer to the first element of the array. Right? So realloc will reallocate a previously allocated block of memory for you. Right? How do you use it? So first of all, you call malloc or calloc, you get back a pointer. Right? When you decide that you want to resize that block of memory, you pass that pointer to realloc, and you ask it to give you back a block of memory having that new size. Right? If the size is smaller than the existing block of memory, the elements at the end of that, whatever is sitting at the end of that block of memory gets chopped off and thrown away. Right? If the memory is bigger than the old chunk of memory, all of the objects that were in your chunk of memory are still there in the same place, and you have extra memory in your block of memory. Okay, so conceptually what happens is the following. Right, so realloc allocates a new block of memory for you, having that size. Right? It copies all of the old objects, all of the objects from the old block of memory into the new block of memory. Right? It then frees the old block of memory, right? And it returns a pointer to the start of the newly allocated block of memory for you. Right? So that's the model of what happens. What actually happens depends on how malloc is implemented by your operating system. Right? And so what actually happens could be very different than that, but as far as you're concerned, that's what happens. Right? You get back a new chunk of memory of the appropriate size. It has all of your objects in it that were there before. Right? That still fit into your new chunk of memory. Right? The old block of memory that was allocated to you gets freed and returned back to the operating system. You still have to free the new block of memory, right? So it's still your responsibility to free the block of memory that realloc returns. Okay, so here's an example. I've used malloc to allocate a string that can hold 4 characters. Right? I put the string sysc into that array. Right? If you print out the array, you're going to get sysc. Right? I now decide I would like to put in a course number, so 220 or something. Right? So I reallocate my previous string. Right? So I call realloc, I pass in the pointer that was returned by malloc, right? And now I ask for more memory. So I'd like 8 characters now, not 5. Room for 7 characters, not 4. Right? Don't forget, null terminator has to go at the end. Right? Here I'm actually checking, right? Realloc returns null if it fails. So here I check. Right? Again, on Linux, this is probably pointless. Right? Oh yes, so what should you do in this case? Right, okay. So remember, realloc returns back a pointer to the reallocated block of memory. If you want to still use str as the name of your string, right? What you should do is you should reassign str so that it now points at the newly allocated, the reallocated block of memory, right? If you don't care about keeping str, you can just use temp, right? But usually you want to reassign your old pointer so that it now points at your new block of memory. Right? I can now put the value I can now concatenate 220 onto the end of the existing string, right? And then print the new string, right? So this is going to print sysc and then sysc, right? When you, after the reallocation, right, the string sysc is still sitting there, right? Finally, after the concatenation, you have sysc 220, right? And again, always a good idea to deallocate or to free the memory, free your allocated memory when you're done with it. Okay, finally, what does free actually do? Well, it releases memory that was allocated by malloc, calloc, or realloc. Right? You can pass it null, in which case it does nothing. Right? So passing it null is always safe. What you can't do with free, though, is that you can't pass in the same pointer more than once if you don't reassign the pointer. Right? So in other words, if you write free p and then on the next line write free p again, that results in undefined behavior. Right? For that reason, people who are concerned about security always say that you should, once you free a pointer, you should always set that pointer to null. Right? And that saves you from the double free bug. Right? Right, so you can't free a pointer more than once. You can, however, free. You can always pass in null. So if you reassign p to be equal to null after you're done with it, and someone accidentally frees p again, everything will be fine. Right. But basically, things to remember: don't free a pointer twice. Right? It leads to undefined behavior. Okay, and so there's the basics of memory dynamic memory allocation. Right? And so the next lecture, which we won't start today, is we're going to implement a string, our own string data type. So instead of using C's arrays of characters, we're going to manage strings ourselves. We'll be able to increase the size of a string, decrease the size of a string, concatenate strings, and all sorts of other stuff. Right? Everything you would expect from a modern string, well, not everything, many of the things that you would expect from a modern string implementation. When we do this, we're basically implementing a list, right? A string is essentially a list of characters. And so if you can implement a string, you can also implement a list using an array in C, sorry. So even though this is called a string data type, it's basically a list data type. And so we'll look at that in the next class, which I guess is Monday. Right? Everybody knows, right? Monday, 10:30 class is canceled, right? So if you have a 10:30 class, it's canceled